Hi, everyone, and welcome to today's webcast. So today we'll be talking about how we can get value from machine learning and artificial intelligence when we're limited by our available data. We can get started by taking a quick look at our topics for today. So we have a pretty straightforward agenda. We'll start with some introductions to ourselves and to Thorogood. We've called the webcast Machine Learning with Limited Data, so we'll level set on what we mean by this and in what ways our data can be limited. From there, we'll look at the impact of data limitations on machine learning and AI applications. And finally, we'll get to steps we can take to get value from these ML and AI activities despite those limitations. Right, so let's begin with some introductions. My name is Scott Stieritz, and I'm a data and analytics consultant at Thorogood. I'm joined today by two of my colleagues, Utkarsh and Mani. The three of us work from our US offices, and we'll talk about Thorogood's locations a bit more in just a second. Utkarsh, Mani, and I, among nearly all of our team members at Thorogood, are focused on working with our customers to understand their business problems and to apply data and AI-focused approaches in helping to address these problems. And this challenge of having limitations in available data sets is something that can come up pretty often, so the three of us are excited to dig into it some more with you all today. As far as Thorogood's an independent specialist data and analytics consultancy. Within data and analytics, our consultants are experienced across the areas of data engineering, data science, and data visualization. And all of our services similarly span this breadth of the data and analytics space. So everything from architecture, design, and implementation to specific solution design and development to hands-on advanced analytics and data science services, all the way through to things like user empowerment and training in key data and analytics topics for the people in our customers' organizations. We're a global organization, so I mentioned that Utkarsh, Mani, and I are joining today from the US, where we have offices in both Philadelphia and Boston, and we have other offices globally in London, Singapore, Sao Paulo, and Bangalore. I mentioned that we're an independent consultancy, so we're therefore not tied to one specific technology. Rather, we have experience across a range of technologies within the data and analytics space, which allows us to understand the business goals and unique situations of our customers in combination with our experience in the technical possibilities to identify the optimal data and AI solutions given the business cases. I've put just a sampling of technologies that we commonly work with, among many others, up on the screen. And like I said, we've kept introductions short, so now let's dive into it. What are we talking about when we're working with data that is limited? I'll start with a diagram of a tabular data set here, but of course it's worth noting that the data that we work with in machine learning and AI applications may not always be tabular, not always structured. Anyway, in our data set, we have a number of different attributes or characteristics which describe whatever we're observing, which are represented by columns in the data set, and we'll call these features. And we then have the observations themselves, in this case, individual rows in our data. When working in machine learning, it's useful to break up this data set into two or more subsets, which we'll call splitting our data. And here we'll have a larger portion of the data going into our training set and the remainder into our test set. Oftentimes, we'll split the data further to have a validation set as well. But this splitting allows us to get a good sense for how well the machine learning solution will perform on new data that we'll encounter in the real world. So we'll take that larger portion, the training set, and use it to train our machine learning model. That is, we'll allow the model to learn from the patterns that it can observe within that training set. And then we'll use the test set, which the model hasn't yet seen, to pass through the model to evaluate how well that model is really performing. Now, what are we talking about when we say that we're working with limited data? Well, we're saying that the quantity or the quality of the data that we have available limits the effectiveness for use in machine learning and AI applications, at least without some further intervention. And these limitations could take a number of different forms. We could have too few observations, so too few rows, as we had seen before. We could have incomplete data or incomplete records, where certain characteristics of our data might not be consistently captured or consistently populated. So we have features with missing data. We might have inaccurate data, where the values that we have don't, or at least no longer represent reality. Could have minimal feature variation. So we want to use our data to learn the patterns between the available input features of our model and their impact on our predicted target variable. But if we have features which have little or no variation in their values across different observations, this won't be very helpful in identifying new or identifying these underlying patterns in our data. And finally, we could have minimal data attribution, where we only have a few attributes, a few features that are captured for each observation, and we're therefore missing out on some of the patterns which might be contained in features that we haven't collected yet. Anyway, there's a variety of ways in which our data can be limited, but for today, we're going to focus in on this first one, in which we have too few observations. We always talk about working with big data, but in this case, what happens if our data is too small? And going back to our diagram from the previous slide, if we don't have enough observations, we'll be limited by the size of our training set or our test set, or most likely both. So why does this matter? Well, let's consider our full population and not just the data that we have available or the data set in front of us, the full wider population that exists out in the real world. In any machine learning application, we're going to have to take a subset of this full population represented in our data, which we'll call our sample. So there's already trimming down of the population into the sample. We only have a certain number of observations, and we can only be so detailed in representing those observations and features. And as we discussed, we'll further split that sample into training and test sets. So the key question here is, as our data has been trimmed down so much relative to the original population, how well have the patterns that are truly present in that wider population been preserved all the way down through sampling and into the training and test sets? In general, we can expect that we'll do a better job of preserving the patterns into the training and test sets as we have more data. But why is this even the key question? Why does it matter if we preserve those patterns? Well, in our training set, this means that our models will have more of an opportunity to learn from and capture these patterns to better represent what's going on in nature. And in the test set, we'll have better representation of the underlying patterns, which will allow a more comprehensive evaluation of whether or not the models that we've built will do a good job in predicting new data that we haven't seen yet. So let's look at a basic example here. Why does more data generally mean better representation of underlying patterns in our population? So for this basic example, let's consider a pharmaceutical company running a clinical trial. And we're comparing the effectiveness of two treatments, which we'll call treatment A and treatment B. And we've captured some data about whether patients' illnesses respond successfully to treatment by either of those two formulas. Now we've captured some data and we can see the success or response rate for patients receiving each treatment. Of course, looking at this simplified data set here, we can see that treatment A has been successful in achieving a response in 100% of our observed patients and treatment B in 0% of our observed patients. But this is a little bit of an exaggerated case. And I hope the issue here becomes pretty obvious. We only have two observations. Will treatment A always be 100% effective? Hopefully, but probably a little unlikely. And treatment B, which might be the best available therapy outside the new treatment A, is it really seeing success in achieving a response in 0% of our patients? Again, probably not. So we could say that we at least suspect that the patterns that exist out there in the real world aren't perfectly captured by our data. Now let's think about capturing a bit more data. As we have a few more observations, and we can start to see what's probably a slightly better representation of the underlying patterns, we can now see that treatment A isn't 100% successful in achieving a response. It's now sitting at 75%, and treatment B at 25%. And those percentages will probably move some more as we continue to collect more and more data. It's also pretty unlikely that the only thing that we want to capture about our patients is which treatment they received. There are probably many more tests and measurements and observations, all of those that we can capture about our patients. And I've represented that here in this example by just adding in the sex of our patients. And perhaps we get further into this trial and we start to suspect a pattern based on what we're seeing for these two treatments. The patients of different sexes respond differently to each. Now, if we ignored this pattern entirely, we may be ignoring some of the key drivers that are out there in nature and overly simplifying our models. But if we try to account for this pattern within a machine learning model, we can see that we'll pretty quickly run into an issue which we had already encountered all the way on the left-hand side of the screen. So let's ask ourselves a question about response rates by treatment and sex. And for our new treatment, treatment A, how often are we successfully getting a response in females? But here's the issue. We only have one observation in this cross-section. The only thing we can read from this is that treatment A is 100% successful in achieving a response in females. But again, is that realistic, or have we just not yet captured enough about the underlying patterns in that cross-section? So as we try to get our machine learning models to account for all of these patterns and more detailed patterns that exist within the wider population, they become increasingly hungry for data. They want more observations across more cross sections of our population. And I realize this is a really simple example, but I hope it makes this clear. ML and AI approaches want data in large volumes, and when we don't have it in large volumes, that can create some challenges. So we'll now pass it over to Utkarsh to give a few more practical examples of when we might run into these issues, and to give some detail as to the specific types of challenges that this limited data can cause.
Now that we've gone over what limited data is and what it looks like, I'm going to be going over some of the challenges that limited data can cause. But first, I'd like to go over some of the real-life examples of where limited data can occur and to give some context for those challenges. So the reason why we have limited data is for one overarching reason, is practical limitations. So these are limitations in the amount of data in the data set due to blockers in real life that prevent more data from being gathered, or no previous applicable data exists, which causes the data set to be small. So the first example of this is an unexpected event. In most cases, if a model is being created using data, there's usually some historic data available, so the model can be made using a larger data set. However, what happens when that event has never occurred before? There is no historic data to look to, and there's only the little data gathered from this singular event. One example of this is forecasting done during the COVID-19 pandemic. Such a large and impactful global event has not occurred in the last 100 years, so there's no time series data that companies can use to forecast during the pandemic. This meant that companies had to forecast using 6 weeks of data, for example, instead of years of historic data to look at. Next example is survey data. Data that has to be gathered from surveying people has its limitations in the fact that the people need to be surveyed. They have to be willing to take the survey, and when they are willing to take the survey, they have to be willing to give all the information that we ask for them to provide. So an example of this is consumer data. Data that comes from consumer surveys won't have many records due to the fact that customers need to voluntarily give companies this information, and participation is usually low. Since the population of data from these surveys is small, the sample used from these machine learning models, as Scott mentioned earlier, will be even smaller and very limited. So the last example is that in general, the data may be limited just in the population of data that can be sampled. Sometimes the data set in general is just limited by the parameters of a study, for example. This occurs frequently in medical studies where the trial itself may have just been 200 people. It would be difficult to gather a good random sample from such a little amount of data. Also, if there's an abundance of medical data, it could be very expensive to purchase, which could limit the records available in the population. Furthermore, some data sets for very rare diseases have very few records, since very few people have that disease. The population is very small again, so the sample taken from this population is going to be small and limited as well. So now that we've given some context for limited data, I thought that I'd go into some challenges caused by limited data, and the biggest challenge overall is overfitting. So small data sets are prone to overfitting, where the model memorizes the training data rather than learning meaningful patterns. So we can see on this graph on the left, you can see that the machine learning model is tracking the pattern of the data that's in the data set, while over here, the overfitted model is just memorizing all the data points. So this model is memorizing all the data points in the data set rather than actually learning the meaningful pattern that is actually deeper in the data set. So they work well on the training data, but poorly on new unseen data. So the model will also be more sensitive to outliers and noise. All data sets contain noise, and models trained on small data sets are more likely to learn the noise since there are so few data points that may not be representative of the population. The next example is difficulty with evaluation hyperparameter tuning. Evaluation is an important step of the machine learning lifecycle since it gives an unbiased estimate of performance on unseen data. With small data sets, it may not make sense to retain such a large test set since most of the data will be needed for training. A small data set will likely not be a representative sample of the population, so the performance estimate will be biased. And so this idea extends to hyperparameter tuning as well, since that becomes challenging with small data sets because there are fewer data points to assess the model's performance accurately, and hyperparameters require model performance to be evaluated on those hyperparameters. Going forward, some other challenges caused by limited data is the bias and unfairness in the model itself. So small data sets may not be representative of the population that they're sampled from, and unrepresentative samples have a high chance of being biased. So if the available data is not representative of the true underlying distribution, the model may inherit these biases present in the dataset, leading to biased predictions. So the bias that we have in this initial data may perpetuate through to the training and test data and then into the model as well. An example of this is in a startup company that wants to do retargeting ad campaigns on Instagram. If their customer base that has purchased through Instagram ads is very small, the sample is likely not representative of the total population of possible users on Instagram. This can mean that the retargeting campaign is likely not going to be effective. And the final challenge, testing and validation challenges. So it can be difficult to divide a small data set into training, testing, and validation test sets while ensuring representative splits from the sample and the population. This can affect performance of the model as well as the reliability of that performance evaluation. So after all of this information, even with these challenges and examples of limited data, this small amount of data is still better than no data and can still be used to make relevant and useful conclusions using some of the methods outlined in the next section, which Mani will go over.
Thank you, Utkarsh. Now that we've seen some challenges that come up when training machine learning models with small data sets, let's take a look at some techniques that can be used to try and help mitigate these challenges. There are 6 techniques that we'll discuss today: model selection, feature engineering, data augmentation, synthetic data generation, transfer learning, and cross-validation. We'll go into these in more detail. And one thing that I do want to point out is that you don't need to use all these techniques when you're working on a data science project with limited data. The techniques that you use, they're just going to depend on your specific problem, and you'll see that as we go through each technique in detail. All right, let's start with model selection. This is going to be the simplest technique that you can try, and it should probably be one of the first things that you try before moving on to more complex methods. When it comes to ML with limited data, simple models and Bayesian models tend to work very well. And by simple models, I just mean models that don't have many parameters. We discussed that small data sets, they're prone to overfitting. And because that simple models, they're just going to help prevent that overfitting because they just have less parameters and therefore less complexity. And on a similar note, the priors that are used in Bayesian methods, they're a natural form of regularization. Next is feature engineering, which is another simple technique that you should try before moving on to more complex methods. Having informative features, it helps when it comes to training any machine learning model, but it becomes more important when dealing with limited data. We discussed how small data sets can have limited variation, which it's going to make it more difficult to identify patterns in the data. So having informative features, it can help make up for this. Now let's move on to data augmentation. Data augmentation is when you create new data by altering the current data set. This is commonly used in image processing with techniques like flipping, rotating, and adding noise to images. This results in more training images, which can help create a more robust model. The next technique we're going to talk about is synthetic data generation. This technique is similar to data augmentation, except that in synthetic data generation, we don't create new data by altering the current data. Instead, we train models on our data and generate entirely new data. So these methods, they work for a wide range of data, including tabular data. And in case you're just wondering of tools, the synthetic data vault is a Python library that kind of hosts a lot of these synthetic data generation models. I do want to point out that since synthetic data has not been observed, caution should be used when deciding to use it in real-world problems. You should always use statistical tests like KS tests to validate whether the synthetic data is similar to the real data. Let's move on to transfer learning. Transfer learning is commonly used on unstructured data. It involves leveraging the features learned from a large data set to your specific machine learning problem. And this is a very powerful technique since you don't need to start from scratch. So let's say you want to classify products as luxury or not luxury based on the product descriptions. If you use transfer learning, you can pick a model that's been trained on a large corpus of text. So it's already learned feature representations for word, sentence, grammar, syntax, etc. And from there, you can train a few layers on top of the model on your specific data set and leverage the general language features that the model's already learned. Lastly, let's talk about cross-validation. Cross-validation is helpful for properly evaluating machine learning models, especially those trained on small data sets. In traditional ML problems, we would split our data into train, test, and validation sets. But with a small data set, this may not be feasible. But in cross-validation, you train a model several times using different parts of the training set and test set at each iteration, and that allow you to train and test your model on the entire data set. So you just get maximum data usage, which is going to be very important when you have a small data set. I wanted to briefly touch on a fairly new technique called few-shot learning. Few-shot learning is a meta-learning technique, which means learning how to learn to solve a problem. It enables a pre-trained model to generalize over categories it hasn't seen during training. You can see an example of a few-shot classification problem on the screen. We give the model a task, examples, and labels as a prompt. So you can see the task here for each product review, describe its sentiment, and then we give it various examples and labels for it to solve. And what this does is we basically give the model context, which in this case, instruction examples on how to solve our specific problem. And now with this information, the model should be able to follow the prompt and give the expected output, which in this case is the sentiment. In addition to text, few-shot learning can be used on a variety of unstructured data like images and audio, although that's not going to follow this prompt format. I didn't discuss this with the other techniques since few-shot learning is still very new and it's not widely used in production. However, advancements in this research area seem to be happening frequently. So I thought I'd just mention it here, and you'll likely come across few-shot learning while doing research, so I just thought it would be a good thing to mention. Now we're coming to the end of today's webinar, so I thought I'd just conclude with some takeaways. Having a large enough training data set is important for a model to be able to learn the underlying patterns and trends in the data, which is going to allow the model to generalize well on unseen data. Small data sets are going to be prone to overfitting, evaluation challenges, and bias during the machine learning lifecycle. Model selection and feature engineering are the simplest techniques that can be used to mitigate the negative effects of limited data. Cross-validation, it's going to enable you to train and evaluate on your entire data set. And it's important to evaluate synthetic data by using statistical tests to compare it to actual data before bringing it into your machine learning project. Lastly, with a small data set, you may not be able to perfectly predict outcomes, but you can still learn a lot of valuable trends and patterns in your data if you use some techniques to help mitigate the effects of having a small data set. All right, thank you everyone for joining today. I hope that you found this webinar useful. Have a nice rest of your day.